Hello, my name is Alan Meier, and I will be speaking about saving energy in unoccupied buildings. More specifically, I will be speaking about saving electricity in briefly unoccupied buildings. But first, I want to acknowledge Kurt Kornbluth, Sadia Gul, and Josh Moorjohn, who contributed the research, paper, and to this presentation. Intuitively, we would expect that electricity use in buildings would increase with the number of people inside it. Similarly, electricity use should decline as the number of occupants falls. Of course, electricity use will never go to zero because of necessary health, safety, and security requirements. The reality is very different and looks quantitatively or qualitatively like this orange wedge. The gap between the ideal relationship and reality represents the potential energy savings. In this presentation, I'm going to focus on the extreme situation. That is when nobody is in the building. In other words, when buildings are vacant. This vacancy may persist for an hour, a month, or even a pandemic. You might ask, what is responsible for this high electricity consumption? We've conducted many audits, and here is a partial list. This is a challenging list of equipment because their consumption ranges from large to tiny. There's also no entirely satisfactory word to describe them. We use MELs, that is miscellaneous electricity loads, because it seems to accurately capture the whole universe of intended products. But honestly, I like the term MELs because the acronym sounds pleasant to the ear. Standby power is one component of MELs energy use, but many of these devices are actually operating in their normal modes because they don't know that nobody is present to use their services when the building is empty. In the future, it will be much more difficult to think of buildings as either occupied or unoccupied. Instead, we need to treat occupancy as a continuum. Here are three potential causes for variable occupancy. The pandemic caused enormous changes in building occupancy, but less so in energy consumption, or at least in North America. One survey of office buildings, admittedly a special segment, found that energy use fell on average less than 30%, even though they were mostly empty. A more detailed study of the Empire State Building, an iconic office building, found only a 28% reduction in electricity consumption, even though 95% of the normal occupants were working at home. This electricity use did not include space heating, cooling, or lighting because they were supplied centrally. It was electricity used by the tenants for equipment and appliances. More about that later. One might not ordinarily think of climate change affecting building occupancy, but it has happened in California several times in the past few years when smoke from nearby wildfires covered the region. The air quality was the worst in the world for at least a week, and the campus was closed. Other kinds of air quality events can affect occupancy too. We're pretty certain that new work practices may result in reduced occupancy. Zoom, Teams, Skype, and other platforms have reduced the need for physical presence in the workplace. Many companies are already reconfiguring their offices in recognition of projected variable occupancy patterns. Now I will turn to the situation at UC Davis and many other locations. UC Davis knew it had a problem with high electricity use in vacant buildings several years before the pandemic. However, the pandemic brought it front and center. The top figure shows the plot of Wi-Fi connections for the whole campus over time. These kinds of data are now collected at many universities and locations. The orange line is 2019 and the blue line is 2020. You can see the decline in Wi-Fi connections even before the campus officially shut down and then dropped quickly to a small fraction of 2019 levels. In contrast, the change in electricity consumption is almost invisible. That's the difference between the black and green lines. In the end, occupancy fell over 90% at UC Davis, but electricity use fell only 15%. This situation was the reason for us to embark on a case study of UC Davis buildings. In the first step of our study, we examined the electricity consumption of different buildings while in normal, occupied mode, and then compared it to the lowest consumption recorded. Most buildings' electricity consumption did not fall much when they were empty. Only one building used less than half of its peak electricity when it was unoccupied. Of course, some of the buildings were laboratories and would be expected to have high continuous electricity from ventilation, refrigeration, and other laboratory facilities. From this list, we selected one building for more detailed examination, that is to say, Giedt Hall. Here's a picture of Giedt Hall. It consists mostly of lecture halls. I put an arrow pointing to the audio-video rack in that lecture room because we'll discuss that soon. They are present in every lecture hall and classroom on campus. And here's the Wi-Fi and electricity data for Giedt Hall for the period covering the spring break. To be sure, electricity use does fluctuate with occupancy, but energy use, while nobody is present, or at least nobody with smartphones, is still very high. Even more surprising was the causes of electricity use in this unoccupied building. The AV equipment was responsible for about a third. The network equipment room followed closely behind. Keep in mind that nobody was in the building using either the AV equipment or the networks during this time. This discovery prompted a closer study of AV equipment energy use at UC Davis. We employed several techniques to find which devices were hot or energized. In some cases, we had to use an infrared camera to identify the highest consuming components because the campus IT department would not let us switch them off or unplug them. But the IT department also helped us measure electricity use of some racks. One of the unexpected findings was that the newer racks use much more electricity than the older racks, both in on and off modes. For example, the Gen 1 unit drew 100 watts in operation and 60 watts in idle. The newer models, the Gen 4B, for example, drew 680 watts and also a small difference less, 615 watts in idle. So the latest AV racks may provide many new and valuable services. However, improved energy efficiency is not one of them. Our energy conservation strategy followed from these kinds of investigations. And led us to develop a new energy conservation strategy, namely focus on the extreme case of zero occupancy. We think that this strategy makes sense for campus buildings and probably for many other buildings because, one, greater electricity savings occur because we can substantially cut back on level of services. There's no hot water required, no chilled drinking water. So a lot of electronics can be switched off. We can even throttle the Wi-Fi service. Second, nobody is in the building to complain when the equipment is switched off or reduced. And finally, there's a vacant situation persists for many hours in a typical year. So a potential for annual significant savings exists. But this strategy only works if we can reliably identify when the building is truly empty and we can switch off equipment during those times. More about that in a moment. You might be skeptical about the opportunities for saving energy when nobody is in the building. Here's a partial list of the measures we are considering. This is a diverse list, but that's the nature of miscellaneous loads and why it's so hard to develop a strategy to reduce them. The middle column describes the modifications that we envision are needed to achieve those savings. In practice, we are creating a new vacancy mode. It's kind of like a sleep mode, but informed by external knowledge. That's different from common sleep modes that are simply based on elapsed time since last activity. It also includes many devices not presently having sleep modes, such as uncontrolled ventilation fans and circulation pumps. Note the large savings fractions. That's because we can be much more aggressive in lowering or even switching off some of these services. Now, after explaining the target and potential savings, I want to describe our technical approach. Zero occupancy is a unique condition from both a sensing perspective and in terms of energy savings potential. We can't tap the potential savings unless we are confident that the building is empty. 3 innovations are needed to shift equipment into that vacancy mode described above. First, we need a means of inferring vacancy. The problem is that while we have occupancy sensors, there's no such thing as a vacancy sensor. Instead, we have to infer vacancy. The inference must be expressed in terms of a confidence or probability, instead of the certainty of most occupancy sensors. A vacancy inference engine needs to continuously compute this probability of vacancy from the stream of sensors, schedules, and other sources providing inputs. The second innovation is a vacancy signal that can be broadcast through the building. Actually, it's a vacancy confidence level rather than a simple yes or no. Finally, the device needs to be modified to respond to the vacancy probability signal. I already described the vacancy modes for some devices earlier. However, they also need logic to respond to a designated probability threshold value. The selected probability depends on several characteristics. One characteristic, for example, will be the device's latency. That is, its ability to quickly recover to normal service levels when a person appears. Many electronics, such as digital wall displays, have short latencies and can therefore switch to a vacancy mode even when there is a relatively low confidence in vacancy. This graphic explains the sequence of operations and the role of the 3 innovations. I don't have enough time to describe the logic inside the vacancy inference engine. Basically, it applies sensor fusion methods to Wi-Fi connections, schedules, motion sensors, security systems, and other inputs. It needs to be robust and able to accommodate data gaps and easily accept new inputs. So it's a challenging thing to construct. Our work and our research is focusing on all 3 of these fronts. This is the end of my talk. You don't need to understand the vacancy inference engine, sensor fusion, and vacancy modes. Instead, I hope you will remember these points. First, vacant buildings are an untapped source of energy savings. Second, the category of miscellaneous energy loads, MELs, is responsible for more and more electricity use in buildings. Finally, we need to develop techniques that enable buildings to become more occupancy responsive, and to do that in an automated way that saves energy. Thank you very much.